First of all, before getting into the video, a big thank you to all the people who've subscribed and who've watched the videos. I hope they've been helpful. Thank you. Rules of powers, indices, exponents. What is a power? Look at this expression, c times a to the power of n. That superscript n is the power, the index, or the exponent. The a is the base, and the c, multiplying that, is the coefficient. Some revision on scientific notation. So scientific notation is a way of writing very large or very small numbers. We have a base multiplied by a power of 10, and the base is from 1 to 9.9. So here's an image showing the Earth and the Sun. The distance from the Earth to the Sun is approximately 150 million kilometers. That can be written as 1.5 times 10 to the power of 8 kilometers, or as 1.5 times 10 to the power of 11 meters. Here's another example. If we consider the electromagnetic spectrum, visible light is just a very small part of the spectrum. That's what we can see with our eye. The range of wavelengths which are visible to our eyes is from 380 to 720 nanometers. A nanometer is a billionth of a meter. So we can write that as 380 times 10 to the minus 9, ranging up to 720 times 10 to the minus 9. But if we were to write in standard notation, it would become 3.8 times 10 to the minus 7, up to 7.2 times 10 to the minus 7 meters. So to look at those numbers as they actually are, that would be 0.0000038, ranging up to 0.0000072. So it's much easier to write these using scientific notation. And here's the final example that we'll look at. The speed of light. The upper bound for speed in the universe that we know is 299,792,458 meters per second. So that can be written as 2.9 times 10 to the 8 meters per second in scientific notation. Now, in the first example, we looked at the distance from the Sun to the Earth, which is 1.5 times 10 to the 11 meters. And because we know the speed of light, we know the distance, we can calculate time. Time is equal to distance divided by speed. So if we divide the distance by the speed, we get a figure of 500 seconds. That's the 1.5 times 10 to the 11 meters divided by 2.9 times 10 to the 8 meters per second, 500 seconds, which is 8 minutes 20 seconds. That is the time it takes light to travel from the Sun to Earth, even at 299,792,458 meters per second. Here's an example. 2 to the power of 2 is equal to 2 times 2, which is equal to 4. So the little superscript 2 means that we have the number 2, the base 2, multiplying itself twice. Here are some further examples. 2 cubed, or 2 to the power of 3, is 2 times 2 times 2. So we have 3 lots of 2 multiplying themselves, which gives us 8. 2 to the 4 is 2 times 2 times 2 times 2. 4 lots of 2 multiplying themselves, which is 16. 2 to the 10, 10 lots of 2, which gives us 1024. And 2 to the 24 is 24 2's multiplying themselves, which gives 16,777,216. 2 to the power of 24, which is that number there, 16,777,216, is the range of color that's displayed in true color, or 24-bit color, and is also apparently the number of colors that the human eye can distinguish between. The next number I want to look at is this, 2 to the power of 64, and from that we subtract 1, which gives this number, which is read as 18 quintillion, 446 quadrillion, 744 trillion, 73 billion, 709 million, 551,615. This number represents a very particular number of things. and we'll have a look at what it represents in the next slide. I'll move this number to the top of the screen and now introduce a chessboard. Consider how many squares there are on a chessboard. 8 by 8, 64. If we put 1 grain of rice on the first square, and then we successively double the number of grains of rice on each successive square, how many will we have? Well, on the first square, we've got 1, which is 2 to the power of 1 minus 1, which is 2 to the 0, which is 1. The second square, we have 2, which is 2 to the power of 2 minus 1, or 2 to the power of 1, 2. On the third square, we have 4, which is 2 to the power of 3 minus 1, or 2 to the power of 2. On the fourth square, we have 2 to the power of 4 minus 1, or 2 to the power of 3, which is 8. So by the time we get to the 64th square, we'll have 2 to the power of 64 minus 1, or 2 to the power of 63, which is 9 quintillion, 223 quadrillion, 372 trillion, 36 billion, 854,775,808. To work out how many grains there are in total on all squares of the chessboard, all we need to do is double that number and then subtract 1. So that means we're looking at 2 to the power of 64, and then from that we subtract 1. And that is the number at the top of the screen. To visualize how big this number is, take a look at these two pictures. On the left, we see a picture of the Earth. And if we consider the equator of the Earth, which those red arrows indicate, the equator is approximately 40,000 kilometers. And on the right, we see an image of a grain of sand on a fingertip. Now, the diameter of such a grain is approximately 0.05 millimeters. Converting those into the same units, what we get is the circumference of the Earth is 4 times 10 to the 10 millimeters, and the diameter of that grain of sand is 5 times 10 to the minus 2 millimeters. Now, to see how many grains of sand it would take to go around the circumference of the Earth, around the equator, all we need to do is divide that small number into that huge number. That means 4 times 10 to the 10 divided by 5 times 10 to the minus 2. When we do that, the answer is 800 billion. That number down the bottom. And the last step here to show just how mammoth that number is at the top, beginning with 18, I'm going to divide that number by 800 billion. The answer is 23 million. What does it mean? It means that the number of grains of sand that we need to go around the entire equator of the Earth, that number, if we multiply it by 23 million, that means if we line up grains of sand to go around the entire equator, we could do it 23 million times before we reach that number at the top of 18 quintillion. That's how big that number is. The last number out of interest that I'll be looking at before we get on to the actual rules of powers is this one here, 2 to the power of 168, which is that number there. That's the largest known power of 2 that doesn't contain all 10 digits from 0 to 9. Ironically, it does not contain the digit 2. First rule, a to the power of m times a to the power of n is equal to a to the power of m plus n. So when we multiply the bases, the same base, we add the powers. Example, 2 to the 4 times 2 to the 3 is equal to 2 to the 4 plus 3, which is 2 to the 7, which happens to be 128. So let's work that out. 2 to the 4 is 16, 2 to the 3 is 8, 16 times 8 is 128. So let's look at why that is. A to the m is a multiplying itself m times. A to the power of n is a multiplying itself n times. When we multiply the first group by the second group, we have a total of m plus n lots of a multiplying themselves. Hence, that can be written as a to the power of m plus n. Second rule, a to the power of m divided by a to the power of n is equal to a to the power of m minus n. So, example, 10 to the power of 6 divided by 10 to the power of 2 is equal to 10 to the power of 6 minus 2, or 10 to the power of 4, which is equal to 10,000. So let's check that. 10 to the 6 is 1 million. 10 to the 2 is 100. 1 million divided by 100 indeed does equal 10,000. A to the m divided by a to the n. So, what we could think of is a quotient. When we divide something by something else, we have a quotient. So we have a numerator and a denominator. The numerator is the first expression, a to the m. That's a multiplied by itself m times. The denominator is the second expression, a to the n. That's a multiplied by itself n times. Now, as with any fraction, a common factor in the numerator and denominator will cancel. So, some of the a's in the numerator will cancel with some of the a's in the denominator. We end up with a difference. That's the key word, a difference of powers, hence the m minus n. Looking at this example over here, we have 3 multiplied by itself 4 times in the numerator and 3 multiplied by itself twice in the denominator. So we have 3 to the 4 over 3 to the 2. And as we can see by cancelling, 2 of the 3's in the numerator cancel with 2 of the 3's in the denominator, leaving 2 3's multiplying each other in the numerator. Hence, 3 squared. 3 to the 4 over 3 to the 2 is 3 to the 4 minus 2, or 3 squared. Third rule, a to the 0 is equal to 1. A not equal to 0, otherwise we have 0 to the 0, which is undefined. So why is it the case that something to the 0 is equal to 1, not 0? Well, think of a to the 0 as a to the power of m minus m, because m minus m is 0. Now, following the previous rule, a to the power of something minus something is just a to the power of the first index divided by a to the power of the second index. So we have a to the power of m over a to the power of m. Anything which is non-zero divided by itself is 1. Fourth rule, a to the power of negative something is equal to 1 over a to the power of the negation of that index. So a to the minus n is equal to 1 over a to the n, where a is not 0. Why is that? Well, a to the power of negative n is equal to a to the power of 0 minus n. So we're utilizing the rule that we established before, where we have a to the power of a difference in our indexes. So when we have that, we have a to the power of 0 minus n is a to the 0 divided by a to the n. And as we saw directly before, a to the 0 is 1. So we have 1 over a to the power of n. Fifth rule, a to the power of m in brackets to the power of n is equal to a to the power of the product, a to the power of mn. So let's look at why this is. A to the m to the power of n means we have a to the m multiplied by itself n times. Below the arrow we have n groups of a to the m multiplying each other. Now if we split each of those groups of a to the m into component parts, we have how many a's? We have m a's in each of those groups, and everything is being multiplied. So we have m lots of a in the first group, m lots of a in the second group. How many groups? N groups. Therefore we have n times m lots of a, hence a to the mn. Here's an example. 10 cubed, that is 10 to the power of 3, all of that to the power of 3. According to the last slide, that is 10 to the power of 3 times 3, which is 10 to the power of 9. So let's check that. 10 cubed is simply 10 cubed times 10 cubed times 10 cubed. 3 groups of 10 to the power of 3. That's equal to, each of those groups is 10 times 10 times 10, and we have 3 of those. So that's 1,000 times 1,000 times 1,000, which is 1 billion. That's a 1 followed by 9 zeros, which indeed is 10 to the power of 9. Sixth rule. The nth root of a is equal to a to the 1 over n. So let's take an example. The second root, or the square root of 16, is equal to 16 to the 1 over 2. Well, what does that mean? It means what number multiplied by itself twice gives 16? Well, something times something is equal to 16. We happen to know that that's 4, or negative 4. Here's another example. The fourth root of 16, which is equal to 16 to the 1 over 4. That means what number multiplied by itself 4 times gives 16? Well, we happen to know that that's 2, because 2 times 2 times 2 times 2 is 16. So the fourth root of 16 is 2, or, in this case, negative 2 also. So the nth root of a means the number multiplied by itself n times that gives a. Seventh rule, open bracket, a times b, close bracket, to the power of m is equal to a to the power of m times b to the power of m. We notice, first of all, that we have m groups of a times b. So we have ab times dot 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 times ab, m lots of a times b. Now, because multiplication is commutative, that means we can swap the order. 4 times 5 is equal to 5 times 4. So a times b is equal to b times a. Now we can group all of the a's together. So we have m lots of a multiplying each other, multiplying m lots of b multiplying each other. So looking at the first group, we have a to the power of m, second group, b to the power of m. Hence, bracket a times b bracket to the power of m is a to the m times b to the m. Some examples. Open bracket, 5x, close bracket, to the power of 3. That's 5 to the power of 3, 5 cubed, times x to the power of 3, x cubed. 125x cubed. Next example. Open bracket, 0.1 w, close bracket, all to the power of 4. Well, that's 0.1 to the power of 4, w to the power of 4. 0.1 is 1/10. So that's 1/10 multiplied by itself 4 times, or 1 over 10,000, or 0.0001 times w to the 4th power. Next example, open bracket, 27y, close bracket, to the power of 1/3. Don't forget, when we have anything to the power of 1 over something, that means it's the somethingth root of that quantity. In this case, it's going to be the third root, or the cube root of 27y. But we're jumping ahead. First of all, that's 27 to the 1 over 3 to the 1/3 times y to the 1 over 3, y to the 1/3. Now, what number multiplies itself 3 times to make 27? Because that's the cube root of 27. That would be 3. 3 times cube root y. Last example, open bracket, 2 times 3, close bracket, to the power of 3. That's equal to 2 cubed times 3 cubed, which is equal to 8 times 27, which is 216. Or we can simply go 2 times 3 is 6, 6 cubed, that's 6 times 6, 36 times 6, again 216. Eighth rule, open bracket, a divided by b, or a over b, close bracket, all to the power of m is equal to a to the m over b to the m. So, let's look at why that is. Well, that's a over b to the power of m. So that's a over b multiplied by itself m times. So m groups of a over b. Now, what we can do is we can simply gather the numerators together. So that's a, m lots of a, all over b, m lots of b. So we have a to the m in the numerator over a to the m in the denominator. Some examples. Open bracket, 5 over 2, close bracket, to the power of 3. Well, that's equal to 5 to the power of 3 over 2 to the power of 3, which is equal to 125 over 8. Next example, open bracket, 3 over 10, or 3 divided by 10, close bracket, to the power of 4. That's equal to 3 to the power of 4 over 10 to the power of 4, which is equal to 81 over 10,000. Next example, open bracket, x divided by y, x over y, close bracket, to the power of 1/3. Now we're raising it to a fractional power. Because it's 1 over something, that means the somethingth root of that expression in the brackets. So, x to the 1/3 over y to the 1/3, which is equal to the cube root, or the third root of x, over the cube root, or the third root of y. Next example, open bracket, a times b squared over c, close bracket, all to the power of 3. Now we already have a power attached to one of the variables inside the brackets, so we follow one of the previous rules. Well, that's equal to a cubed b squared to the power of 3, which is b to the 2 times 3 over c cubed, which is equal to a cubed b to the 6 over c cubed. Thanks very much for watching. I hope that that's been useful. Keep looking at the channel for more videos, and like and subscribe if you found this useful. Thank you.